So, second speaker today is Anibal Medina from Max Planck and Università di Roma, Paris. In fact, Anibal gave a course on TDA for our master students last year, and he promised to talk about Steenrod operations, but there wasn't enough time. So,
yeah, promise made, promise kept. So thank you very much for the invitation. I'm very happy to be presenting some of my work to you guys. And before we get there, let me pause here for a moment. All for today is going to be to describe this new computable invariant called Steenrod barcodes. And it's a strict generalization of the usual barcode that we know and love. And just to give a little taste, this is the kind of applications that we're going to encounter. Here we see two spaces. I'm going to return to this example with more details later on. And I'm computing here usual persistent cohomology up to dimension 3. And those resulting features appear here as circles, the same on this side. There's a new feature that distinguishes this two persistent diagram, which is this diamond here. And this is the new invariant that we're capturing, that it is present in this space, but it's not present in this other space. Okay, I want to return to this. But we need to develop some theory before we get to the computation side of it all. First, philosophy. Let me state the viewpoint that I'm going to be taking, some of the motivations that I have. Well, first is to state what is one of the goals that I have, and I think it's shared by many people in algebraic topology, since it's so broad, to construct invariants of spaces up to some notion of equivalence. And we can fill in many options for those key words, but today we're going to be focusing on CW complexes and homotopy equivalence. The basic tension about this invariance, and it is well known how computable versus how much information they carry, how strong the invariant is. The example that we use to illustrate this tension is cohomology versus homotopy. I'm quite familiar with this. But I would like to focus today on a more subtle tension, and that is between the constructions of the invariants, how effective those constructions are versus how functorial the constructions turn out to be. And to illustrate this tension, an example that some of us might know well is to define cohomology effectively through chain complexes, or to define cohomology through homotopy classes of maps to Eilenberg-MacLane spaces. The first one is effective, not so functorial. The second one is extremely functorial, but not effective at all. So how do we define cohomology effectively? Well, chain complexes. But where do those come from? An idea of Poincaré taught us to break spaces into contractible pieces. So there's a key idea. We tend to use simplices cubes as the contractible pieces that we use in this cellular decomposition of spaces. This idea was pushed forward further by Cannon-Quillen, replacing spaces by functors with geometric realizations. You might have heard of simplicial sets, cubical sets. Again, they're all assembled from these basic pieces. And in order to compute their cohomology, we will effectively compute it via a chain complex that is assembled from the chain complexes associated with basic pieces. The chains on the standard simplex, the chains on the standard key. And what are the goals for today? We're going to focus on the standard pieces, the standard examples, and understand them quite closely, in particular the diagonal map, and extract from this understanding effective, sometimes called local, computations of finer invariants of cohomology. So before we get there, let's highlight some of the shortcomings of looking at cohomology just linearly. As graded vector spaces, here's two spaces that cannot be distinguished just by their mod 2 Betty numbers. The real projected plane and the wedge of a 1 sphere and a 2 sphere. So their union over 1. These two spaces are clearly different. They are not homotopy equivalent, but cohomology as graded vector spaces is not a strong enough tool to separate. That is due to the choice of coefficients. If I choose different coefficients, I would be able to distinguish them, and that is true. But then, let me give you this example. The complex projected plane and the wedge of a 2 sphere and a 4 sphere are spaces whose homotopy types are certainly different, but their cohomology as graded abelian groups is not strong enough to distinguish. And then you will say, well, there's more information that is available to us that can distinguish them. And that is the so-called product structure, or cup product structure in cohomology. And that's a very important invariant that is going to be playing a role in this talk. Additional cohomological structure comes from, in an effective way, actually comes from an explicit chain approximation to the diagonal of standard synthesis. So this was the original definition of Alexander and Whitney. We defined the cup product by dualizing an approximation to the diagonal. And I should mention also that Cartan and Serre have an explicit chain approximation to the cubes, so covering the two examples that we're carrying with us. And that's a very beautiful invariant. But let me push this train of thought and first introduce this classical construction, the suspension of spaces, here illustrated with the suspension of a circle. We have 2 points and then we join them with all the points in the original space, in this case the circle. Now with this construction, we can produce 2 spaces. Now the suspension of the previous 2 spaces that I discussed that are certainly not homotopy equivalent, but that they cannot be distinguished by cohomology with the cup product structure. So they are indistinguishable using cohomology considered as a graded plane. But they can be distinguished if we consider the action of the Steenrod algebra and cohomology. And this is what I'm going to be talking about today. I should mention that in this contrast between effective constructions and functorial ones, we can define Steenrod operations, or the action of the Steenrod algebra in the spectral, the functorial, more functorial side, almost by definition, right? But what we're interested in today is to make those constructions effective, to make them explicit, and to eventually incorporate them into the persistence pipeline. So, how explicit can we make such construction? And this goes back to the foundational work of Steenrod in the 40s, that he noticed that any chain approximation to the diagonal breaks an intrinsic symmetry that the diagonal spaces has, flipping the factors. So since I'm illustrating here the chain approximation to the diagonal of the interval, this generator, the one-dimensional generator in the domain, is sent to the sum of these 2 generators, right? Because there's no generator here in the middle. That would be what we send it at the level of spaces. But when we pass through chains or cell structures, we break that symmetric property. And from this broken symmetry is that the Steenrod operations, or the action of the Steenrod algebra, comes from. To correct this breaking of the mod 2 symmetry, of the S2 symmetry, I should say, Steenrod introduced explicit maps. We can think of them as higher diagonals. The delta 0, it's the same as that introduced by Alexander and Whitney, but we have this additional diagonals, which are of higher and higher degrees, that interpolate between the 2 options that arise after breaking the symmetry. Because we can look at this picture and say, well, instead of taking this image, or that generator, we could have taken the sum of these 2 generators as the image. And those 2 are related by the broken symmetry. And this delta 1 would be interpolating between those two choices. Right? So we can see here, what is the boundary of delta 1? Would be 1 minus the transposition of delta 0. So we can think of delta 1 sending this generator to the two-dimensional generator here, whose boundary is the difference between the two options. Okay, so this is what this higher deltas do, because they don't stop just correcting the broken symmetry of delta 0. They themselves are not symmetric. So delta 2 corrects the breaking of the symmetry of delta 1, and so on and so forth. Right, so coherent correction up to homotopies. And once we have this structure, which is defined, I want to insist on this, at the chain level, we can extract this celebrated structure at the cohomology level, the Steenrod squares, which are endomorphisms of cohomology with mod 2 coefficients, which are defined by this formula. We take a cocycle representative and we send it to the cohomology class represented by this cocycle. So it eats chains and should produce a number. So we apply the diagonal to that chain and then evaluate it against the cocycle times itself. Okay, this is where the original construction comes from. This is what we're going to explore more closely. And so the kind of additional structure that we're detecting, or that this invariance can detect, I would like to just give an example that is more geometric. If we use point rate duality, in certain cases, the Steenrod squares detect self-intersection. So, for example, we have a model of the torus, a model of the claim bottle. We know they're not homotopy equivalent. We also know that mod 2 cohomology has graded vector spaces is not strong enough to distinguish them, but the Steenrod squares are able to distinguish them. The rank of SQ1 for the torus is 0. The rank of SQ1 for the claim bottle is 1. But what is this 0 and 1 measuring? Well, in this case, that can be quite geometric in the explanation. It's measuring the self-intersection of the homology class, the homology class represented by this blue line. So how do you compute self-intersections? You perturb them. So here is a perturbation, but there's no intersection. But if I take a perturbation in the claim bottle, I'm always going to have an odd number of intersections. And mod 2 that odd number is this one that we're capturing. So this is the intuition of what this additional invariant is carrying in this particular geometric setting. But we have a whole family, SQ1, SQ2, etc. So what do we need in order to be effective? We have to have usable description of this higher diagonals of Steenrod. And I would like to present one now. I'm not going to present the original one of Steenrod. But before I can do that, I need to introduce some notation. So if this is a simplex, v0 to vm, d sub u, where u is an integer between 0 and m, is going to give us the codimension 1 simplex obtained by removing the vertex in position u. This is the so-called the face map. Now this set, p raised to n sub q, again, two integers, is going to be the collection of subsets of integers between 0 and n, whose cardinality is q. Very straightforward.
It's a huge,
huh?
It's a huge collection.
It is the size that
It's n choose q.
Now, for any element in here, we're going to take its elements and order them. There's no problem with doing that. And denote d sub the subset to be the composition of the face maps of the elements that this subset contains. Okay? The last piece of notation I'm going to introduce is the following. U raised to either 0 or 1. This is going to be a pair of subsets of U that form a partition of U. And the subset U raised to epsilon contains all the elements whose sum, whose position plus its value, it's 0 or 1 mod 2. Okay, so this is giving me a split between the elements of any U in this collection. And with this notation, introduce a description of this delta I operations. We're going to sum over this subset, and we're going to split the elements that we're summing over into the 0 and the 1 part and act on this simplicity. Okay? It's a very simple description, especially if you know Steenrod's original description. And I'm going to return to the question of if these two agree or not later on. In principle, they don't need to agree. The only thing that I need is that this satisfies the homological equations that I showed before. That the boundary of delta I is 1 minus t delta I minus 1, and they do satisfy that. I would like to maybe illustrate this with an example that is potentially familiar to some people. What is delta 0? That's just the Alexander-Whitney diagonal applied to this two-dimensional simplex. We see playing this game that we split things in this way. So we have three cardinality 2 subsets of the set 0, 1, 2, and they're split in this way according to the rule that I described here. And if we see the action that they have is this one, which, as I'm stating, might be familiar with some people, but this is the actual Alexander-Whitney. Okay, fine. We have this new description. What is it good for? Well, it's good to compute Steenrod squares fast. Let me, before I present the algorithm, let me do the comparison with the existing tool, an implementation in Sage of a method due to Gonzalez, Diaz, and Real. The implementation was done by John Palmieri. Here, what I'm going to do is to compare the execution time of these two methods, and they're both very simple methods. They're both just Python implementations, no optimizations done. They're equal footing. And I'm only intervening the Steenrod square step. And on the x-axis, you see these numbers that correspond to the number of simplices of models for higher and higher suspensions of a real projected plane. So with no suspensions, the real projected plane can be modeled with 32 simplices, the suspension with 74 simplices, and as we move here, you see that the number of simplices roughly doubles every time we take a suspension. And well, the comparison speaks for itself. It's much faster. Now,
in which dimension are you computing SQ1?
Yeah, I'm only computing it.
Oh, okay,
and the only
one.
So the orange line, it's probably not constant though.
Well, no, I would have to change the size to be able that it's actually going up.
Okay.
But I do want to maybe say a couple of things about why it's apparently so much faster. So again, I don't expect to analyze this too closely, but I do want to emphasize a couple of things. The input is going to be the support of the co-cycle representative. So here we're going to have a number of simplices. The simplices where the co-cycle is 1 and non-zero. And then we're going to run over all pairs, actually ordered pairs. Right? So it's actually quadratic on the length of the input. But where it actually gains a lot of speed is that it computes like a universal support for the co-cycle representing the Steenrod square of this class. And that universal one it doesn't depend on how big the space is. So the number of simplices of the space doesn't play much of a role in this. Okay? And then we just check that this universal thing is or is not part of the X. Whereas the other methods kind of reverse things and they iterate over all the simplices on X. So they're much more sensitive to the number of simplices of X, whereas this method is much more sensitive to the length of the co-cycle representative. This is why I was so excited about Barbara telling us yesterday that she can find representatives in cohomology whose representation in the column form is quite sparse, because that will speed up this, which is currently our bottleneck. Okay, moving on. If you guys don't have questions. So what are Steenrod barcodes? Now we have a method to compute Steenrod squares quickly on simplicial complexes, and we would like to incorporate this additional information into the persistent pipeline. So let me review some of the basics. We have a filter simplicial complex, and applying cohomology, I'm interested in cohomology here, we obtain a so-called persistence module, whose barcode is a summary of the way many numbers are shared consecutively by the different modules. So we obtain something like this. What the naturality of Steenrod squares buys us, that it gives us an endomorphism of this persistence module, right? And as you might know, this is a very good category, the category of persistence module. It has kernels and images. So in particular, we can take the image of this endomorphism to obtain a new persistence module. And the barcode of that persistence module is what we define to be the Steenrod barcode, SQK barcode. Okay? Here's where I will say something that's a bit cheeky. SQ0 is the identity. Right? So the image will be the original. So SQ0 barcode is just the usual barcode. So it's a strict generalization. Although that's not the way that you will compute the usual the usual barcode. But
Depends on the coefficients.
It depends on the coefficients. Very good observation. That's right. With mod 2 coefficients. And the other thing that we care about is, well, is this new invariant, this new barcode stable? And this is work in progress with Li, Zhu, and Facundo. Okay, so this is the definition. Any questions? I would like to. Oh, yes.
Yeah. I was just wondering if it's possible. Is there like a so the idea is that you're splitting up all different modules for each K, right?
Yeah.
Is there a way to have like a persistent thing where you have like the Steenrod squares as part, like all together in one kind of like giving like almost an algebra structure on it?
Yeah.
At the level of persistence modules.
Yep.
Or is there some like fundamental reason?
No, there's no fundamental reason. So it's a typical choice of, am I going to think of this as a graded persistent module or a bunch of persistence modules related to it? And here I kind of chose to put them all together, but I chose to keep the K free, but I could have perfectly keep the K all together. Yeah.
Is there somehow between this notion of barcode, there is the idea that the barcode of the image of SQK contains all the information about the SQK? Are you losing information that you could also have by keeping the whole map of SQK and doing a barcode about the map rather than about the image?
I don't know. I'll have to come back to you with that. So let me return now to that example that I started with. And it comes from taking filtrations of two contractible spaces. Right? So the contractible spaces that I'm going to consider is the cone and the suspension of these two spaces that I mentioned before can be distinguished only by the Steenrod action. It's not only by that, it can be distinguished by that, but not by the ring structure or the Betty numbers. Okay, so I just take some filtrations, some models, random order of the simplices as long as it is a filtration, and this is what we get. As I showed before, if you remove this diamond, I don't think we would be able to distinguish those two spaces, even if we're keeping cohomology up to degree 3. But as long as we introduce this diamond, which comes from computing SQ2, we're able to distinguish this to enhance persistent diamonds. Okay? Yeah.
Do I see some points in the diagram?
Yeah, there's a bunch of points.
Okay.
And actually there's a Steenrod point in the diagonals.
Okay.
Right, that's an SQ1 that's around. but away from the diagonal, yeah, and as you're noticing, the diagonal is covered with marks.
Oh, I thought it was just big. Okay.
Yeah. So this is the way the diagonal will look without any points.
Okay.
The rest are just magic. Yeah, and you know, artifacts. Okay. So, how do we compute this then? So there are 3 steps. So the first one, we heard beautiful presentation from Barbara, is based on having this type of decomposition. I'm going to be using the anti-transpose boundary matrix, and through column operations obtain a reduced matrix that can be expressed as a product of the original anti-transpose boundary and an invertible upper triangular B. From here, we can read off cohomology representatives and build a new matrix. And for each entry, is going to have a representative of the Steenrod square apply to the cohomology class that represents. And so we have this new SPK using the algorithm I showed earlier. Right, so this algorithm was explained by Barbara. This algorithm is the one that I compared with Sage before. And the third step is to use R, thought of as a basis of generating coboundaries, to reduce Q. And we're going to do this systematically. So we have an additional reduction step. Okay, this is pretty fast. This is pretty fast. This is pretty fast as long as the support of the cocycles is not crazy long. The bottleneck occurs usually when we have 1 or 2 cocycles that are represented by extremely long cocycles or columns. So anyway, and just to show how simple the third step is, this would be the type of pseudocode that will describe. So we keep track of what Steenrod squares in Q are alive, and the barcode is empty, and we're going to iterate over the filtration, reducing using larger and larger chunks of R, larger and larger chunks of Q. That's essentially what we're doing. After I saw your talk, I said, oh, we should actually put those matrices there and show how the evolution is. I'll take it for next presentation. Okay, and this is pretty computable. So we went ahead and implemented it. This is with the help of Umberto Lupo and Guillaume Tesson, fellow members of the Giotto team. And this package is written. We have 2 implementations, a C++ implementation that hasn't been properly tested, and we have a Python implementation that has been cheated, I think is the term, just-in-time compilation, using Numba. It runs pretty fast. And that Python package is available by just using this command. And we are accepting contributions, and this post URL. Also every. And I would like to come closer to an end by showing the use of this technique in a more concrete real-world example when it comes from analyzing spatial conformations of the cyclooctane molecule. This is a point cloud living in R24. Every point in the point cloud keeps track of the 3-dimensional coordinates of the 8 carbon atoms. So 8 times 3, 20. And it was proposed that a certain part of this point cloud concentrates along measure that is concentrated along a claim body. And we offer more evidence to that guess by showing that, yes, the persistent absolute cohomology barcode, as was already computed, has 2 one-dimensional features and a one-dimensional two feature. But furthermore, that there is a non-trivial twisting between one of these one-dimensional features and this two-dimensional feature expressed by this bar here. Right, so more evidence about this being the claimed bar. So this would rule out another manifold that would fit in here, the torus.
So here, you don't assume anything about the structure of these bonds, of these carbons and so on. You are just looking at plausible ones. The one that could happen hypothetically.
I don't know. We just took this data set.
Oh, okay.
I'm not familiar with the specifics apart from what I already mentioned.
Okay, thanks.
Okay, so this is supposed to be the high point of the talk, saying, hey, Steenrod barcodes are there in nature. We have the tools, it's fine. But before I have that sales speech, I would like to take a moment to say, well, what else is out there? So we already saw Steenrod squares, but it turns out that Steenrod squares are just the beginning of higher structures in the same spirit that are present with odd prime coefficients. Those are Steenrod operations. And I would like to remind us that Steenrod squares come from the broken symmetry of the binary diagonal, right? X goes to X times X. So we have coming from hierarchy diagonals. X goes to X times itself P times. And this structure is there, and it was defined only through group theoretic means. So it was not effective construction. And so again, this tension that I started talking about, the tension between effective constructions and functorial constructions. Up to very recently, we only had functorial constructions for these higher Steenrod operations, and they play a very important role. And I want to say that all the structure of cohomology stably is captured by this. Right? There's nothing else that is stably invariant. So they're quite important in stable homotopy. But in those contexts, people didn't care about effective constructions. We care about them, and some physicists do as well. So we wanted to build in this gap, and we define generalizations of the kappa higher diagonals, but for odd P operations. And very explicit. So much so that can be implemented. And I did that in this computer algebra system, CH, also open source. And I would like to just show the shape of the kind of output. So cap 3, this is the prime 3, in degree 2, applied with this 0, 1, 2 guy, will be a sum, as presented here. Notice that now we do need coefficients. So there's some minuses appearing here and there. And there are triples of simplices, because we are in P equals tensor products. Okay, so that's for the future. I don't know if this is going to be relevant for TDA. It might depend on what kind of implementations we find, but that is work in progress.
So, for example, for the P equals 3, then your algorithm is going to be cubic in the length of your cycle.
Potentially, yes. That's right. Yeah. So that will be one of the first things to notice. That yes, you're right. Okay, so that's for the future. So let me just come back to a close and summarize what we talked about. So here's the slogan. Homotopy theory. This is a slogan that I usually present to homotopy theories. I guess I don't need to highlight it so much here. But homotopy theory requires additional structures to be used concretely. And since we care about using it concretely, we need effective constructions. Today, we focus on Steenrod operations. In particular, we define Steenrod barcodes. They can be defined equally for any prime, but I just chose to define them here for P equals 2 because they are more computable given the current technology. And I also introduce a tool to extract this barcode from a typical persistent pipeline to enhance, I would say, the typical persistent pipeline. And I show that this is kind of a proof of concept, right? That this finer invariants are out there. Okay. So the challenge now becomes to find data sets where this invariant is also present, and through domain-specific explanations, what's the meaning of this very important topological twisting that now we have access to. And with that said, thank you for your attention.
Can you go back to the reduction, the matrix reduction you perform, the image of the square? Maybe it's not important, but is it dependent on the generators you find for the co-boundary reductions?
Yeah, that for sure.
So you don't need to show that you are independent from them.
Oh, any co-cycle representative will work well.
Okay.
Will give the right answer. Smart choices of co-cycle representative might speed up the process. Right. So where is the dependency on the choice of the co-cycle representatives? It comes into this queue.
Yeah.
So Q was built by applying to a choice of co-cycle representatives for the standard bars. This algorithm that computes a co-cycle representative for the Steenrod square. And so the first dependency is there. But we have theoretical guarantees that any co-cycle representative will play well in this third step.
So it doesn't affect the barcode. Of course, it does affect the computations.
That's right.
Yep. Yeah, so I think the persistence module stuff is like seemingly started to find some applications in like
Is that a little louder?
the persistence module stuff. So people have started to try to apply that to other areas of like pure mathematics. I'm just wondering if you have any ideas about maybe the structures of these like persistence modules of the image of Steenrod operations. Maybe are there any kind of applications in more theoretical math that you can imagine that this would be useful, where you see, spaces or shapes where the Steenrod operations are more easily variable?
Yeah, for sure. That's a good question. And recently with Bauer and Maximilian Schmal, we actually extended some of the techniques to context of more general functionals, with the domain of this real value function, which doesn't even need to be continuous. It's infinite dimensional. So there, the key application that we deduced from that study was to be able to impose Morse inequalities on the space that we were considering in this functional space. So I would not be surprised, although I haven't thought too hard about it, that we can have Morse type inequalities incorporating higher topological invariants like the one I'm describing.
Any questions? No? Let's thank Anibal then.